Welcome to lesson 3.4, computing actual areas from a scale drawing. It's your first video lesson. How cool is this? I'm sorry I can't be here to go over the lesson with you, but really, it's just like me being here when you're watching it. So for our bell ringer, we have to find the length of a scale drawing or actual length given the scale. So the first one, we have 1 centimeter to 6 millimeters. So if I have 3 centimeters, how many millimeters am I going to have? Well, 3 times 6 tells me I'm going to have 18 millimeters. Okay. Now looking at the second one, notice that our x value, our very first unit here is not a 1, so we need to change that. So if we have 4 inches and 12 feet, remember we're used to doing y over x. So we have 12 feet is 4 inches. 12 divided by 4 is 3, so that means it's going to be 3 feet per 1 inch. Okay, so really my scale is 1 inch equals 3 feet. But what happens if I have 8 feet? Well, if I have 8 feet and 3 feet is an inch, how many inches do I have? Well, 8 feet divided by my 3 feet for 1 inch is going to tell me just that. So when I do it, I'm going to get 8 feet times 1/3 is 8 thirds. So that means 8 thirds inches is going to give me 8 feet. Huh, that's pretty cool. All right, number 3, I have x and y. Remember, it's not per my 1, so I need to change that. So y over x equals 27 meters over 3 centimeters. That means that my scale is really 9 meters over 1 centimeter. So I can rewrite it like this. 1 centimeter equals 9 meters. Well, if 1 centimeter equals 9 meters, how many meters is 6 centimeters going to equal? Well, to do that, we just multiply, right? We have 9 meters over 1 centimeter times my 6 centimeters that I'm looking for. My centimeters cancel. I get 54 meters total. So 6 centimeters is 54 meters. All right. Now let's look at our objective for today. Our objective is to compute actual areas from a scale drawing. So think to yourself, when would you ever have to compute an area based on a scale drawing? Well, maybe when you're building a house, right? And you have your scale drawing and you want to have a room be a certain size, but on paper it's super, super tiny, right? Like this. But then in real life it's huge. So to know the area on the small paper will help us with the area of our actual house, like on our blueprint, right? So that's what we're going to talk about today. But first, I want you to try to guess, how many cheese balls do you think will fit on this tray? Take a moment, pause the video, and guess. Welcome back. How many did you think there were? Well, if I take this little one and I try to line it all up really carefully, there are actually 286 cheese balls on that tray. The easiest way to figure that out was to actually line up your cheese balls on the left or right, and then on the top or bottom, right? And then if you know how many cheese balls line the sides, to figure out how many cheese balls fill the whole thing, you would just multiply your length times your width to see how many cheese balls you had all together. That would probably be the easiest way to guess instead of actually counting each time. All right, flip the page for me, please. So we have to remember some area formulas before we get started. So the first area formula is L times W. Well, Miss Wall, that's length times width. Hello. Right? Length times width is the formula that we use when we are finding the area of a rectangle. Right? Or a square if you want. What about area equals 1/2 base times height? Where do we use that? Let's set the area formula up. Well, it's the area formula of a triangle. Okay? So we're going to use these two formulas a lot today. Now, in order to find the area of a shape, we're going to have these basic steps that we have to follow. The first is that we're going to have to change all the measurements to the actual size, if it's not done so already. Then we're going to have to write the formula for the area, right? So this is the area formula. Then you're going to have to substitute all your values into the area formula. So you're going to have to substitute in your length that you have, your width that you have, and then you're going to actually figure out the area. So let's take a look at the first one. It says, use the diagram below to find the scale factor. Then find the area of each figure. All right, so for the scale factor, we have to do the scale drawing dimensions over the original. So just by looking here, looking at the actual picture to the new one, how many times bigger did it get? Is the scale factor going to be bigger than 1 or less than 1? Well, it got bigger, which means our scale factor is going to be larger than 1. How many times bigger? If I went from 3 to 6, I'm getting 2 times bigger, right? So our scale drawing, when we do our scale of 6 units over our 3 units, we get 2. So our scale factor is 2 because both the sides are getting 2 times bigger. 3 times 2 gives us 6. 4 times 2 gives me 8. So now I have to figure out what the actual area is. So starting off, I'm going to write, well, this is a rectangle, so the area is length times width. So that means my area, if my length is 4 and my width is 3, I'm just going to write over here L equals 4, W equals 3. I'm going to do area equals 4 times 3, which is going to be 12 units squared, right? Remember, your units are squared when you have area because you're multiplying 2 length values, okay? So that's our actual area. But now I need to do the scale drawing. So I have area, it's still the same. I'm writing my equation, length times width. My area, now my length is now 8, and my width is now 6. So my area is 8 times 6, which is 48 units squared. Wow, this is interesting. Check it out. This is 12, and this is 48. How many times bigger is the scale drawing area compared to the actual? Well, to figure that out, I'm just going to do my scaled over my original. So I have 48 over 12. That's 4. So my scale factor is 2, but my area is 4 times bigger than the original. I want you to think about that, okay? And when you see me tomorrow, if anybody can tell me why it's 4 times bigger instead of 2 times bigger, maybe I'll get a special little treat. All right, so now let's take a look at number 2. Use the diagram below to find the scale factor, then find the area of each figure. Okay, so we're dealing with some triangles here. All right, when I look at the actual picture and then the scale drawing, I can't quite figure out what they multiplied 9 by to get me my 12. It's got to be something that's not a whole number, because I know that 9 times 2 is 18. That's too big. So let's try to figure it out. So our scale factor, we do our scale drawing over our original. So you could pick. You could do 12 for your scale drawing, but then remember to pick the corresponding side. So if you pick the height of the scale, you have to pick the height of the actual. So my height of my actual is 9. 12 divided by 9, it's not going to give me a whole number. It's going to give me 4/3 if I reduce it, or 1 1/3 if I actually divide them. Okay, so that means my scale factor is 1 1/3. But let's make sure that's true. I want to make sure it's the same for my bases as well. So remember, my base, I have a scale of 8 over 6. 8 over 6 is 4 over 3, which is also 1 1/3. So I know that it checks out that they are proportional. There is a scale factor, and it's 1 1/3. Okay, we're going to use 4/3, though, in the equation below to help us out if we need to. So our actual area, well, the first step that we have to do is change all the measurements to the actual size. Well, the actual picture measurements are already there, so we're okay there. Now we have to write the formula. So the area formula for a triangle is 1/2 base times height. Remember, your base is your bottom number, and your height is how tall it is. So if we have area equals 1/2, my actual picture My base is 6. My height is 9. So I'm going to multiply those. Area equals, well, what's 1/2 of 6? That's 3 times 9. My area is 27. Don't forget to write units squared. So that means my area of my actual triangle is 27 units. But then how big is the area in my scale drawing? Well, we're going to do the same thing, only we're going to use the dimensions of our scale drawing. So the area is 1/2 base times height. I have to write my formula first. Then the area is going to be 1/2. My base is 8. My height is 12. Area equals 1/2 times 8. Well, half of 8 is 4 times 12. What's 4 times 12? 48 units. Don't forget your squared. Okay? I hope you're having fun. I'm having fun even though I'm not there with you. All right, now I would like you to flip the page for me. This next one's a little bit tricky, so I want you to pay close attention. I hope you're paying close attention the whole time, you know. So 3, the triangle depicted by the drawing has an actual area of 36 square units. What is the scale of the drawing? Note that each square on the grid has a length of 1 unit. So if the actual area is 36 square units, I have to figure out what the scale drawing area is. So this right here is not the actual, but they're giving us the scale drawing. So let's figure out what the area of this is. Actually, I have total faith that you can do it. So I want you to pause the video and find the area of this triangle. Welcome back. Your area should have been 1/2 base times height. Your base was 6, your height was 3. So when you simplify that, you should get your area to be 9 units squared. Okay. Now, if we look at the area of our scale drawing versus the area of the actual picture, how many times smaller is the area of our scale drawing than the original? How many of these triangles could I fit into a triangle with an area of 36 square units? 4, right? So I'm going to write this over to the side that the area of the triangle shown is 4 times smaller, or we could say it's 1/2, or not 1/2, sorry, 1/4 the size of the original area. So looking back at our example, looking back over here, right, the area was 4 times bigger, but the scale factor was 2. So looking at this one, if my area is 4 times smaller, then that means my scale factor is really 2 times smaller. So it's really going to be 1/2. If my scale factor is 1/2, that means that for every 1 unit of the scaled drawing really represents 2 units of the original. Now, this question can be a little bit confusing. It's okay. This is a tough one, okay? If you have any questions, we can always talk about it tomorrow. But for time's sake, let's move on to the next one. The next one says we have to find the actual area of the shape below. So we have 3 steps that we have to do. The first step that we have to do is change to actual size. So this gave us the scaled version. We need to find out what the actual area is. So first we have to change those dimensions. So let's take a look. If 1 inch is 10 feet, that means I have 10 feet for every 1 inch times both of my length and my width are 6. So I have 6 inches. I'm going to get 60 feet. So that means in real life, this side length is 60 feet. That also means that this is 60 feet as well, right? So in actuality, if I were to draw my triangle, I'd get 60 feet and 60 feet. So now the second step I need to do is write the area formula. So when we write the area formula, the area of a square is just area equals length times width. Now the third step we're going to do is substitute in the values. Okay, so when we substitute the values in, we get area equals, now we have 60 feet times 60 feet. When I solve it, the area is a total of 3,600 feet squared. So in the real world, the area of that square is 3,600 feet squared. Not too shabby, right? All right. What we're going to do now is looking at number 5. We have to follow these 3 steps. So our first step is we're going to change this triangle to its actual size. So if 1 centimeter is 15 meters, I have 15 meters over 1 centimeter, and I need to figure out what my new base is, right? So I'm going to put B here for base, times my 12 centimeters. Well, 15 times 12 gives me 180 meters. To find my height, I'm going to take my scale, 15 meters over 1 centimeter, and multiply it by my 8 centimeters. When we do that, again, our centimeters cancel. 15 times 8 is 120 meters. So that means in actuality, if I were to find this triangle, that means my base would be 180 meters and my height would be 120. So what I would like you to do now is find the actual area of this. So write your formula for the area of a triangle and solve it through. Pause the video to do so, please. Welcome back. You should have had area as 1/2 base times height. So your area is 1/2, your base was 180, your height was 120. When you plug those in, you should have got the area equals 10,800 meters squared. Okay? All right, flip the page for me. All right, very last question. We've got this. Almost done. So, Vincent proposes an idea to the student government to install a basketball hoop along with a court marked with all the shooting lines and boundary lines at his school for students to use at recess. He presents the plan to install a half-court design as shown below. After checking with school administration, he is told it will be approved if it will fit on the empty lot that measures 25 feet by 75 feet on the school property. Will the lot be big enough for the court that he planned? Explain using the chart. All right, so from what I'm understanding, Vincent came to school administration, maybe like Mr. Straley, and showed him this picture. He said, hey, I want to make this happen on that court out there. Is it possible? Well, the actual dimensions of the court are this big, so we have to do some math to figure out if it is possible and then move forward. So looking ahead, our scale is 1 inch equals 15 feet. So that means our scale factor is going to be 15. Our equation, well, our scale factors are unit rate, so it'd be y equals kx, so y equals 15x. Now, we're going to use this to help us fill in the dimensions over here. So we have 1 inch is actually 15 feet on the court, right? Now, our length is 2 inches. So that means I'm going to have twice as many feet. So I'm going to have 30 feet on the actual court. Now our height is 1 2/3 inches. Oh no, actual court, what do I do there? Well, I have 1 2/3, and I have to multiply by 15, right? So I have 1 2/3 times 15. Woohoo, around the world time. 3 times 1, 4, so I have 5/3 times 15. Can I do bow tie? I think I can. Check it out. 3 goes into 15 5 times. 3 goes into 3 once. Right? I have 5 times 5, which is 25 feet. So I have 25 feet right here. Not too bad, right? So looking at this, if I were to draw my basketball court in real life, it would be 25 feet by 30 feet. 30 feet wide, 25 feet deep, right? So to find the actual area of it, to find the area of a triangle, it's going to be length times width. My area is going to be 25 times 30. So my area here is 750 feet squared. So that's how much room my basketball court that Vincent designed is going to take up. 750, woo, Miss Wall, 750 feet squared. So will the lot be big enough? Well, check it out. The lot was originally 25 feet by 75 feet. So this is mine. This is my vision. Well, really, this is Vincent's vision, right? And the actual dimensions of what we hope to have it be is 75 feet by 25 feet. So just by looking at this and comparing them, will Vincent's vision that he mapped out fit on this court? Absolutely, right? You got it. It's going to definitely fit. So will it be enough? Yes, it will. And why did I make you calculate this area right here? Well, I did it because our objective said to find the area of the actual drawings. Plus, I wanted you to see that, wow, that's actually quite a bit of feet. Okay? So, once again, I'm sorry I couldn't be there with you today. I want you to now take a look at your homework. Okay? One of the things that you're going to do when you look at your homework that I want to help you out with is remembering that after you read the scenario down below here, when you have your scale, you need to make sure that you change your scale so that the first measurement is a 1 before you go any further. So change the scale first where this is a 1, figure out how many feet is for 1 inch, and then proceed through the problem, okay? All right, I hope you have fun. I can't wait to see you tomorrow. Have fun doing some math.